and welcome to another seminar for graduate engineers. This is seminar number 19, but it's part 4 of my series looking at the structural insulated panels, or SIPS. This time we're going to be looking at the capacity of fixings, and we'll be looking at the capacity of bolts, rivets and screws in steel and aluminium, and we'll be looking at our standards 4600 and 1664. And yes, this is another one of those seminars that are saying, what does this spreadsheet do? And we'll have a quick look at the red coat spreadsheets and try to present the answer in Mathcad. And by the way, just because I do it all in Mathcad, it doesn't mean you have to do it all in Mathcad. It simply says that this is how you explain what's going on in the spreadsheet. If you're content and confident that the spreadsheet works, then by all means use the spreadsheet. You should use the tool that's most appropriate for you. A reminder of the full SIPS series. We started with tiny homes and modular houses. We then went on to the structural capacity of panels, looking at roofs and ceilings and walls and beams in structural insulated panels. Last time we were looking at cold stores and freezers, case studies, and this time we're looking at the capacity of fixings. And so yes, there's going to be lots of Mathcad. Next time, and the final time, last of the year, we'll be looking at warm roof load span tables, and we'll be looking at transformed section properties using Mathcad and looking at how we derive section tables and property tables, load span tables using Mathcad matrices. So we're going to be overdosing on Mathcad on our next session. The sources of this presentation. On my left, you have the Australia-New Zealand standard 4600 for cold form steel structures. And on the right, you have the Australia-New Zealand standard for aluminium structures, which is 1664. And yes, we have a spreadsheet for this. So just click on my templates, and under LSF for light steel framing, you'll see a sheet called ASNZS4600. So if you open that, you'll get all of these tiny calculations. Here I'm going to explain what those mean. So this is my Mathcad version of that spreadsheet in effect. So if we open it up, here is the first of the Mathcad sheet. So this is fixing design to ASNZS 4600. We're looking at first at bolted connections to clause 5.3. So we're looking at an M10 grade 4.6 bolt in grade 300 steel to a steel angle. Now the two grades are slightly different. We start with putting in our basic parameters. So here is the diameter of the fixing, the spacing of the fixings, the end edge distance of the connected part. Here is the thicknesses of the top sheet and the bottom sheet, and then the strengths, yield strength and ultimate strengths for the top and bottom sheets. A quick check on the minimum edge distance and minimum spacing from clause 5.3.1. We then look at tear out, and each of these sections has a different capacity reduction factor, which you'll find under each of the clauses. And from that, we have a nominal shear capacity, and then we apply our reduction factor to give us a 4.21 on minimum. Then we look at the section tension of the connected part. So that's a little bit of metal between your fixings that is being put into tension because of the action of the fixings. Bear in mind that your fixings are there to transfer your load from one component to another, and you have to follow the whole load path to find what the capacity is of that fixing. So the equation here is given in equation 5.3.3. and we have quite a large capacity in that little bit of metal still left between the holes. Then we look at bearing capacity in clause 5.4.2. Again, we've got our own capacity reduction factor for this section. We put in a nested if, depending on the ratio between the fixing diameter and the thickness of the material. So the C1 is the C parameter for the top sheet, and the C2 is the C parameter for the bottom sheet. So you get different values because of the thicknesses. So then you get a nominal bearing capacity of the two sheets, and then you take the smallest one and apply your capacity reduction factor. Now we look at the bolt hole deformation, and this is given by the equation in 5343. We take the minimum of the bearing capacity of the top sheet and the bottom sheet and apply our bearing capacity reduction factor. Then we look at bolts in shear. This is probably not the critical element, because what you'll find in fixings in light gauge steel and in aluminium is that it's not the bolt or the screw or the rivet that is the critical component. It is nearly always the metal that you're joining. And so we just take the gross the section area of the bolt and then apply it. So we make up whether it's going to be within the threads or outside of the threads, and add shear planes and the values together to give us our bolt capacity, which is much higher than the bearing capacity or the shear capacity of the material we're joining. Similarly with the bolts in tension, you've seen this sort of thing before, tension area multiplied by your tensile strength with a capacity reduction factor. Again, much higher than the tensile capacity of the material you're looking at. You can combine the two, and the clause in the code allows you a utilization ratio of combined tension and shear of up to 1.1. Now we look at screws, and that's dealt with in clause 5.4. In this case, we're looking at 14 gauge tech screws. Same material, we're looking at steel sheet and a steel angle. So we pull down our values from those components from above. My convention is, if we're repeating an old value, we put it in grey. If it's a new value, we put it in yellow. It's entirely my creation. You can have your own convention if you like. So we're looking at, first of all, a check on the minimum edge distance and the minimum spacing. Then we look at the tension in the connected part again, as we've done for the bolts. And then we look at tilting and hole bearing. And again, we've got that nested if statement to derive the C1, C2 values. And then there's another fancy equation to define what the bearing capacity is. Now, it gives you different equations depending on the ratio of the thicknesses. So if it's less than 1, this is your equation. If it's more than 2.5, this is your equation. Now, what if it's somewhere in between, like we've got? Then you use linear interpolation to derive the actual value. Then you check on the tear out of the shear as limited by the end distance. So we've deliberately put in a small value for our end distance, but we're still having a reasonably large value of your tear out capacity of the material. So that's not going to be the governing factor. Looking at the screws in tension, again, a check on the edge distance. And we're looking at pull out and pull over in clause 4.3.2. And there's a number of different arrangements that they show within this clause. I've just taken a snapshot of one of them. And again, we look at our screw diameter and put in what our washer thickness is and our washer diameter. From that, you get your effective pull over diameter, D-W, And then from that, you get the pullover capacity, what I've called NOV, and then the pull out capacity, NOU. And you'll see in this case that your pull out capacity is the governing factor. Apply our strength reduction factor to that, and you get a value of 1.48. If you're using a top hat, AS NZS 4600 has a special clause just for that. And there's obviously some concern about fixing thin top hat sections, which are usually girts or even purlins for light gauge steel structures. And you pull it out and you've got different equations depending on the material thickness and the material grades as well. If you're looking at the connections combined shear and pullover, there's a utilization ratio factor for that. Again, the clause allows you up to 1.1. However, this is only valid if these conditions are met, and in our case, those conditions weren't met. Look at the connection subject to combined shear and pullout, and again, we've got another equation to put it together, and you're allowed up to 1.15 in a combined shear and pull out. In this case, it is valid because our parameters match the conditions given in the code. Just a quick check on the screws themselves. Normally, again, the screw isn't the weak link in itself. So you can look up in tables what the shear capacity and the tension capacity is. In our case, we've said it's 5 kilonewtons. If we're applying 3 in both shear and tension, we put it together and get a utilization ratio of 1.2. That's okay because the clause in the code allows us the utilization up to 1.3. Moving on to rivets, that's dealt with in clause 6 of the code. And we've picked out a 4.8 millimeter blind rivet, which is quite typical in this application. So we put in our parameters for the rivet diameter and the spacing of the rivets. Again, we're looking at top thickness and the bottom thickness. And we put in the strengths, tensile strengths of the two materials. Start with a check on the spacing, then check the tension in the connected part. Look at tilting, hold bearing. Again, we've got 2 different ways of working out what the design bearing capacity is, depending on the ratio of the thicknesses. Now, in our case, our T2 over T1 is less than 1, so therefore it's going to be the 0.62. Just check if you're going to be limited by edge distance. In our case, we're not. And then we get a final capacity of our rivets in shear. This final one is just to check that you're not exceeding the capacity of the rivet itself. And there are published tables of the shear and axial tensile capacity of, in this case, blind rivets in either steel or aluminium. Okay. So that was the Mathcad calc for our light gauge steel fixings. We then move on to aluminium, and yes, we have a spreadsheet for that too. So click on my templates and you'll find under aluminium, there is a spreadsheet called aluminium formulae. And if you open that, you will see some of the numbers and equations that we're about to show you in the Mathcad. So here's my Mathcad version of it. And again, just because I'm doing it in Mathcad, it doesn't mean you have to, but just because you're using a spreadsheet, you should be understanding what you're doing using that spreadsheet, and don't use them blindly and don't have blind trust in spreadsheets. So one easy way, or not so easy way of checking a spreadsheet is actually to write out the calculation in full. And it's much easier to check a calculation if you've got a full set of references with it. So let's open that Mathcad. So now we're into aluminium fixing design to AS NZS 1664. And we'll start with bolts and rivets because the code puts them together. As before, we pick out our strength reduction factors and our nominal fastener diameter. In this case, it's a rivet. The alloy is quite important. Just saying your material is aluminium is not enough. Aluminium comes in hundreds of different grades and tempers. So in this case, we're using a 6060 T5. This is not a particular strong aluminium alloy, but it's a very common one and often used in trimmings and angles and so forth. So we start again with a check on the minimum edge distance and minimum spacing. Because it's aluminium, there's at least 4 ways of doing almost everything. And so we check the bearing capacity, comparing it to the yield strength and the ultimate strength, and then taking the minimum for both of the sheets. We then move on to bearing on the flat surfaces and the pins on bolts in slotted holes, for example. Now, again, we've got 4 ways of doing it, 2 for each sheet, 2 for comparing yield strength versus the ultimate strength, and then we take the minimum, which gives us our capacity in bearing. We've listed the tensile and shear strength of rivets here, just for reference. And then we look at the tension loads in our connection. And that gives you a minimum tensile capacity of 2.83 in this case. We also look at factored shear loads, which is very similar. Look at our shear area and multiply by your shear strength to give us a shear capacity of 1.63. Now we move on to screws, in this case self-tapping screws. They're usually often self-drilling, self-tapping screws. We'll look at a small screw in this case, the same sort of diameter, it's 4.88. And we have our strength reduction factors taken from clause 5.3.2 of the code 1664. And so we compare our yield and our ultimate tensile strengths, and that gives us our design shear strengths. We take the minimum of all the 4 values. That's looking at tension. Again, we're looking at a pull out and a pull over. So just to remind you, it's not usually the screw, the bolt or the rivet that fails, but the material that you're joining. And in that, when the fixing is in tension, it will either pull out of the underlying material or pull over the fixing from the top material. So in this case, we have a pull out force of up to 2.52 and a pull over of 1.48 using the equations from the code. And the design tension capacity is simply the minimum of those 2 values, and we apply a strength reduction factor to it. Finally, we're often joining steel and aluminium together. Now, there is no spreadsheet for this particular one, but it's basically joining the 2. And this is a common scenario that our steel-faced insulated panels are joined with aluminium angles. And the scenario is such that when you're transferring load from the ceiling to the wall, uplift on the ceiling will put the ceiling rivets in tension and the wall rivets into shear. Similarly, shear in the ceiling will put the ceiling rivets in shear and the wall rivets in tension. So depending on the scenario, your rivet will either be in shear or tension or both. So in other calculations, we have derived the forces within our rivets, but due to the load applied to it. So in our case, we've applied a tensile load of 1 kilonewton per meter and a shear of 1.5 kilonewtons per meter at this junction. So turning first to the aluminium, we're looking at mechanical connectors in clause 5. We pull out our strength reduction factors, put in our basic information like the diameter of the fastener and the spacing. We pull out, this kind time is just for one of them. So one sheet, one element is aluminium, and here are the bearing and tensile strengths given by the code. So our angle in this case is 1.5 millimeters thick. A quick check on the minimum spacing and edge distances. A check on the bearing, which we've seen before. And we compare the bearing capacity against the applied shear and against applied tension. Then we find out the capacity under tension. So we have our design tension capacity, not spelled correctly. And then compare it to the applied tension force and the shear force. We've also already put in the spacing of the bolts. The SF is the spacing of, the rivets. Then look at the shear loads that you're applying and the shear capacity. So you're looking at the shear capacity of the rivet, and it's not usually the rivet that's a weak point, but it's worth checking. Then we go on to the other component. Well, it's cold form steel. In this case, it's grade 300. And you're looking at, again, 4.8 millimeter rivets. So you've pulled down the diameter from above and the spacing from above. And you're looking at the thickness of the sheet. In this case, it's 0.55. Again, a check on the minimum spacing and minimum edge distance. Looking at the tension in the connected part, and you're subject to shear. So you apply those, again, compare them with the applied loading in tension and shear. A check on tilting and hole bearing. And it's a complicated equation depending on whether your T2 over T1 is less than 1, then you get 0.54. If it's more than 2.5, you get 0.94. In our case, it's less than the 0.367, so therefore you're using the first value, even though I've put in the potential for interpolation in there. So our utilization has come through. In shear, it's 82%, and bearing against tension, it's 55%. If you're looking at limiting by end distances, here's the equation from clause 5.6.2.4. And a quick check on the rivet, again, just the rivet itself in shear, not normally a problem. And those are the references. So those are the three main Mathcad calculations for working out the fixings in shear. And obviously you don't have to do all of them depending on your scenario. You just do what is appropriate for your case. A little reminder of some of the useful standards. So there's the NASH standards, which says the National Association of Steel Framed Housing. And this one's in New Zealand, and they publish a series of books. So the NASH standards parts 1 and 2, and there's also the NASH building envelope solutions. These are available from the NASH website for free, and they will email them to you if you ask them nicely. There's also a NASH in Australia, and they're not so nice because they charge you for their books, but this one's quite useful. It's a NASH handbook for residential and low-rise steel framing. And from that book, they have a whole series of tables. So you don't even have to go through all those calculations. You just pick it out of the table. And they have listed for screws, design bearing capacity of a screwed connection in shear. And they list thicknesses and the grades as well. So different values for different thicknesses and different grades of the steel. They do the same for tension as well as bearing. There's also the same set of tables for rivets and for bolts. So worth having a look at. And if you're using materials which happen to comply with their set of standards, it's much easier to pick it out of the table than doing all those calculations. Here are the references, as before. Metalcraft website has some useful information, as does the Concrete and Prof. Holodor websites. Here are the codes of practice that we've been using today. That's the ASNZS 1664. It's rather old and in need of serious updating. For strengths of materials, there's more alloys and more tempers available than are shown in that standard. So contact the manufacturer and they'll point you in the direction of their properties. This one is reasonably new and kept up to date, the NZS 4600 for cold form steel structures. And here are the websites for the associations for steel framed housing, both in New Zealand and in Australia. So our next seminar is on warm roof load span tables, where we do a deep dive into matrices and plots and charts and all sorts of things, looking at a lot more complicated Mathcad. So leave a like and leave a comment and subscribe to the channel. I see from the analytics, our second biggest audience is in Hong Kong. So welcome if you're watching in Hong Kong. If you have any comments, just putting in the comment section under the YouTube video as well.